There was a morning 66 million years ago that began like any other. The sun rose over a world that was warmer than ours, a world without permanent ice at its poles, a world whose continents were arranged differently than they are today. North America still partially separated from South America, India drifting northward toward a collision with Asia that would eventually raise the Himalayas, a shallow inland sea dividing North America from north to south. Puns. In the forests and floodplains of that world, animals moved through the early morning. Some of them were enormous. Sauropods whose footsteps left impressions half a meter deep in soft ground. Theropods whose serrated teeth could shear through bone. Others were modest isons. Small, feathered dinosaurs that would have looked, to a modern eye, something like large, strange birds. Others still were the ancestors of mammals as we know them. Small, largely nocturnal creatures that spent their lives in the shadows of the great reptiles, and cautious and quick. None of them knew what was coming. Approximately 66 million years ago, an asteroid approximately 10 to 12 kilometers in diameter, the size of a small city, entered Earth's atmosphere at a shallow angle and struck what is now the Yucatán Peninsula of Mexico. The impact released energy equivalent to approximately 100 million megatons of TNT, roughly 10 billion times more powerful than the nuclear bomb that destroyed Hiroshima. What followed was the most dramatic single day in the history of vertebrate life on Earth, and the days, months, and years after it were worse. Tonight we explore that day and the days that followed, and what was lost and what was saved, and what ultimately emerged from the catastrophe, including, eventually, us. We have the whole night to explore it. There is no rush. The story is long, and it deserves to be told slowly, parts, as we begin our journey tonight. Let us first understand the world that existed before the impact, because the story of what was lost is incomplete without an appreciation of what was there. The late Cretaceous period, which spanned from approximately 100 to 66 million years ago, was one of the most biologically rich epochs in Earth's history. Planet was warmer today by approximately 4 to 8 degrees Celsius on average, with no permanent polar ice sheets. Sea levels were higher, flooding vast areas of the continental interiors. Shallow, warm seas that covered much of Europe and central North America teemed with marine life. Is ammonites in extraordinary diversity, mosasaurs and plesiosaurs, vast schools of fish and reefs of rudest bivalves. Land, the dominant vertebrates were, of course, the non-avian dinosaurs. The late Cretaceous was not the golden age of the largest dinosaurs that had passed somewhat earlier, but it was a period of extraordinary dinosaurian diversity. Hadrosaurs, the duck-billed dinosaurs, were among the most abundant large herbivores in North America and Asia, gathering in herds that may have numbered in the thousands. Ceratopsians, the horned dinosaurs, relatives of Triceratops, were similarly diverse and abundant. Ankylosaurs carried their armor, plating and tail clubs through the undergrowth. predators were formidable. Tyrannosaurus rex, along with its relatives, occupied the apex predator niche in North America. These were not the lumbering, cold-blooded reptiles of earlier imagination, but increasingly well-understood animals, warm-blooded, possibly feathered, juveniles with sophisticated sensory systems and evidence for complex social behavior. The vegetation was changing. Flowering plants, angiosperms, had appeared earlier in the Cretaceous and were spreading rapidly during the late Cretaceous, diversifying into the enormous variety of flowering plants that dominate land ecosystems today. Forests of the late Cretaceous mixed familiar-seeming flowering plants with ferns, cycads, and conifers. A world in transition between the ancient plant communities of the Mesozoic and the flowering, plant-dominated world we inhabit. This was the world that existed on the morning of the impact. Rich, diverse, ancient, and by any standard we can apply, magnificently alive. Let us follow the asteroid itself, tracing its history from its formation in the asteroid belt to its catastrophic encounter with Earth.
The impactor that ended the Cretaceous was most likely a member of the carbonaceous chondrite class of asteroids, the most primitive class of solar system material,
Composed of the original building blocks from which the planets formed,
containing carbon, water, silicate minerals,
and complex organic compounds. Carbonaceous chondrite formed in the outer portion of the asteroid belt, beyond what is called the snow line. The distance from the sun at which temperatures were enough for water ice to remain solid during the solar system's formation. The object that struck Earth was approximately 10 to 12 kilometers across. Based on the size of the Chicxulub crater it produced and the volume of material ejected. For comparison, the island of Manhattan is approximately 21 kilometers long. The asteroid was roughly half the length of Manhattan, compressed into a roughly spherical shape. In the millions of years before the impact, the asteroid had been slowly drifting in an orbit that, over time, was perturbed by gravitational interactions with other bodies. Small changes accumulated over long timescales, gradually altering its trajectory until it intersected Earth's orbit. This is the normal fate of many asteroids. The vast majority of Earth-crossing asteroids eventually either strike a planet, are ejected from the solar system by gravitational interaction with Jupiter, or remain in Earth-crossing orbits for long periods before being broken up by tidal forces or collisions. This one struck Earth, entered the atmosphere at an angle estimated at between 30 and 60 degrees from horizontal, traveling at approximately 20 kilometers per second, approximately 60 times the speed of sound. At that velocity, the passage through the atmosphere was not a slowing and gentle descent. The atmosphere was, in comparison to the asteroid's momentum, essentially nothing. The asteroid was barely slowed at all by its passage through the air. Entire transit through the atmosphere, from first contact with air molecules at the very top of the atmosphere to impact took approximately 2 seconds. 2 seconds from when someone at the impact site would have first seen a bright light in the sky to the moment the world ended. Or, as we continue our journey, let us follow the impact itself, second by second, in the immediate aftermath. Because the physics of what happened in the first minutes is extraordinary and worth understanding carefully. The asteroid struck the shallow carbonate and evaporite rocks of the Yucatán Platform. This geological detail is significant. The rocks at the impact site were rich in sulfur-bearing minerals called evaporites, gypsum and anhydrite, deposited in shallow marine environments. They also contained enormous quantities of calcium carbonate. The specific chemistry of these rocks would, as we will explore, shape the global consequences of the impact. At the moment of contact, the kinetic energy of the asteroid, approximately 100 million megatons of TNT equivalent, and was released almost instantaneously. The asteroid was not simply crushed, it was vaporized. The rock beneath it was vaporized. The vaporized material expanded outward at enormous velocities, producing an ejector plume that rose above the atmosphere within minutes. Crater that formed, now buried beneath younger sediments and called the Chicxulub crater, is approximately 180 kilometers across. But the crater did not form slowly. The entire excavation process, the displacement of approximately 24,000 cubic kilometers of rock, was complete within roughly 2 minutes. In those 2 minutes, the ground around the impact site was struck by ejecta, raining back down from the plume. The shock wave propagated outward through the bedrock at supersonic velocities, triggering earthquakes of a magnitude estimated at approximately 10 to 11 on the Richter scale. The largest earthquakes in the geological record. These seismic waves propagated around the entire planet multiple times, triggering landslides and tsunamis globally. The Gulf of Mexico, a shallow sea at the time, was struck by tsunamis of extraordinary height. Wave heights of hundreds of meters have been estimated for the immediate coastal regions near the impact. These waves propagated outward into the open ocean, reaching the coasts of the Americas within hours. And let us follow what happened to the material thrown outward from the impact, the ejecta, because its behavior in the minutes and hours after impact was responsible for one of the most devastating immediate consequences. Chicxulub impact produced an ejecta plume that extended above the atmosphere within minutes. Enormous quantities of vaporized and melted rock, along with sulfur-rich gases from the evaporite rocks, were lofted to altitudes far above the stratosphere, some of it achieving suborbital and even orbital velocities. This material, tiny glass spherules formed as molten rock droplets, cooled in the upper atmosphere. Larger chunks of rock and fine dust spread around the Earth in the hours following the impact as it re-entered the atmosphere from above, falling back to Earth from its ballistic trajectories. It heated the atmosphere from above through frictional heating, The heating of the upper atmosphere by re-entering ejecta lasted for tens of minutes to perhaps an hour or two globally. But in that time, it deposited enough heat into the air to raise the temperature of the low atmospheres significantly. Hence, some estimates suggest that the infrared radiation from the glowing, re-entering ejecta was sufficient to ignite fires across North America and large portions of the hemisphere that had direct exposure. The extent of this impact-triggered fire is debated. The geological record does show a distinctive charcoal layer in sediments at the Cretaceous-Paleogene boundary in many locations, evidence that wildfires were widespread. Whether these fires were ignited by thermal radiation from re-entering ejecta, by the spreading of fires from initial ignition sources, or by some combination, remains an area of active research. What is clear is that in the hours following the impact, large regions of North America and potentially other continents were experiencing a degree of thermal pulse, blast of radiant heat from above, sufficient to kill exposed animals and ignite vegetation. In North America, which was closest to the impact and most directly exposed to the ejecta re-entry heating, the immediate death toll among exposed animals was catastrophic. As we continue following the events of that day, let us turn to the process that would ultimately kill most of what survived the initial impact. The shutting off of sunlight. Impact injected enormous quantities of fine particles into the upper atmosphere. These particles came from several sources. First was pulverized rock from the impact site itself. Enormous quantities of fine dust lofted by the explosion into the stratosphere and above. Stratospheric dust settles slowly over months to years because the stratosphere has no weather to wash it out quickly. The second, and ultimately more important, source was sulfur. Yucatán, evaporite, rocks contained massive amounts of sulfur-bearing minerals. When they were vaporized by the impact, they released sulfur dioxide and other sulfur-bearing gases in quantity estimated at perhaps 100 billion tons. In the stratosphere, this sulfur dioxide combined with water vapor to form sulfuric acid aerosols, tiny droplets of sulfuric acid that are extraordinarily effective at reflecting and absorbing sunlight. The third source was soot from the global wildfires that burned in the weeks and months following the impact. Together, these three sources loaded the stratosphere with an aerosol and particle burden that blocked and scattered an enormous fraction of incoming sunlight. Specific estimates vary among studies, but most models suggest that sunlight reaching the surface was due a few percent of normal, or possibly less, within weeks of the impact, and that this reduced light persisted for years. A world with a few percent of normal sunlight is a world in photosynthetic shutdown. Plants cannot photosynthesize in near darkness. Phytoplankton, the microscopic photosynthetic organisms that form the base of most marine food chains, cannot grow without light. Primary producers of nearly every ecosystem on Earth were eliminated or severely suppressed within weeks of the impact. An ecosystem without primary producers does not persist. The food chains built on photosynthesis collapsed, and in the world that followed, eventually something drew its first. Thank you for exploring with us tonight.